Hi everyone, welcome to the third webinar in our 6-part series on alternative approaches for acute inhalation toxicity to address global regulatory and non-regulatory data requirements. My name is Amy Klippinger. I am the Associate Director of the PETA International Science Consortium and will be co-moderating today's webinar with Dr. David Allen, who works as a contractor supporting the US NTP Interagency Center for the Evaluation of Alternative Toxicological Methods, also known as NICETM. I'd like to thank you all for joining this webinar, and before I introduce today's speakers, we'll briefly run through a few logistics. As I mentioned, this is the third webinar in our 6-part series. If you missed the first 2 webinars, I encourage you to watch the recordings, which are posted online at the link on your screen. Today's webinar will focus on in silico methods, and our speakers will describe some of the methods currently in use and under development, highlighting work in progress and data gaps, which will help in developing a strategy to direct future research. The slides from today's webinar and a recording will be posted within a couple days, again at the link on the screen. Everyone is muted now. If you have a technical question anytime during the presentation, you can use the question box, which is located in the panel on the right-hand side of your screen. If you have a question for one of the speakers, you can type it in that same question box. We will hold all of the questions until after both talks, and then David will ask your questions to the speakers during the Q&A period. So please send in your questions anytime during the webinars. Lastly, before I introduce our first speaker, I want to mention the other webinars coming up in this series. The next webinar on the GHS additivity formula will take place on June 28th. You can find more details about this webinar and the other upcoming webinars online. Please note that if you are registered for this webinar, you will automatically be registered for all 6 webinars in the series. But if you use the Outlook calendar reminders, you have to add each webinar to your calendar individually if you want to get those Outlook reminders. Okay, speaking first today will be Dr. Grace Pat Levitch. Grace is currently a research chemist at the National Center for Computational Toxicology within the US EPA. She started her career at Unilever UK before moving to the European Commission's Joint Research Center in Italy and then to DuPont in the US. A chemist and toxicologist by training, her research interests have focused on the development and application of QSARs and read across for regulatory purposes. Today, she will provide an overview of the status of non-testing approaches for acute inhalation toxicology. The title of her talk is A Practical Perspective of Non-Testing Approaches for Acute Inhalation Toxicity, Past, Present, and Future.
Okay, so I hope you can see my screen because I'm still a little challenged with the webinar technology. As Amy's kindly introduced me, I'd want to sort of thank both Amy and Dave Allen for inviting me to share what I feel are my own very brief perspective of what I feel is the status of non-testing approaches with respect to acute inhalation toxicity. And I hope what I provide in this perspective is just sort of paving the way for a much more deeper drive of some of the leading edge work that Dow Chemical has been exploring, and that will be followed in Dan's talk. So onto my outline then. I have kind of a brief outline of what I want to share today. I've started off just with a couple of definitions just to sort of put in a point of context of what I mean by QSAR approaches and TTC, the thresholds of toxicological concern. I want to shift then to sort of talk a little bit about some of the considerations one might have before embarking on any actual experimental testing. So, you know, what might be some non-testing considerations to take place that might waive doing any testing. Then I want to sort of switch again and talk a little bit about what work's been done in terms of the thresholds for toxicological concern with respect to inhalation routes of exposure, and then focus the rest of the talk on some of the in silico tools that are available, focusing on some of the local models, some of the expert systems, and what might be some of the mechanistic hybrid approaches. And I'll kind of finish up with some potential future directions that can be considered, and I think that's paving the way really for what Dan will be talking about afterwards. Okay, so moving on then. I think of, I always sort of talk about non-testing approaches because I think these sort of cover a real gamut of different types of methodologies, from QSARs, quantitative structure-activity relationships, to structure-activity relationships and chemical grouping approaches, including read-across. And all of these are underpinned in terms of how a chemical will interact with a defined system and how that can be linked back to its molecular structure. And we have on one end of the continuum, if you like, sort of the chemical grouping approaches that are a little less formalized in structure versus something that is more structured in terms of QSAR approaches themselves. And to that end, I just wanted to have a quick slide that just outlines what my working definitions of QSARs are for reference as I draw attention to them in the course of the talk. So for me, an SAR, a ZAR, is a qualitative association between a chemical substructure and its potential to exhibit a certain biological effect. And whereas a QSAR is really a statistical established correlation relating some type of quantitative parameter derived from a structure and relating that to a quantitative measure of biological activity. And one can think of expert systems as really being compilations of QSARs or SARs packaged together that enable a ease of use. So a more efficient way of running QSAR models. So moving on then, I wanted to sort of touch on some of these considerations before doing any type of testing. And I think this kind of draws down to really kind of trying to understand something about the substance that you're evaluating. So if something is highly corrosive to skin, that might sort of draw you down a different path of other evaluations to do before any testing. Or there's a role there in terms of looking at positive classifications from acute toxicity derived in other routes of entry, and that might be another consideration. And as well, there are physical form considerations one might take into account when thinking about acute inhalation testing. And I want to draw into each of those in turn just to explain a little bit about what I mean by them. Okay, so if you have something that's highly corrosive to skin, I think this is really relevant to know whether you're going to have some local irritation or corrosion effects in the respiratory tract following a single exposure. And that's kind of relevant to know in terms of, you know, is it meaningful or relevant to actually sort of conduct any sort of testing. So you could derive some kind of evidence from an in vitro skin corrosion test, perhaps, to sort of get an idea of whether your substance is highly corrosive or not. You might use a read-across type of approach, looking at in vitro or in vivo data from related substances. Or you could make use of SARs such as those that are encoded in expert systems and other in silico tools. And all of these together can give you some flavor of whether your substance is going to be highly corrosive to skin and therefore could have some impact in the respiratory tract. Since we're sort of talking more about non-testing approaches, I think it's worth drawing attention to some of the expert systems and in silico tools that have some information encoded about skin irritation and how that relates to structure. And I had one example here that looks at something known as the OASIS pipeline toolkit that's been developed by the Laboratory of Mathematical Chemistry. And really, within this pipeline, there is a module that sort of looks at skin irritation and corrosion rules, and underpinning that are different sort of QSARs for different chemical classes. And under the sort of in the I don't think I can use a pointer on here, but under allergy, one of the sort of boxes there sort of makes reference to a skin irritation corrosion model. There are also what's known as the BFR rule base that was developed by the German authorities, and they also include a number of inclusion rules related back to sort of structural characteristics that can give you an idea of whether something might be classified for irritation and corrosion. Okay, moving on then. Positive classification from acute toxicity derived from another route of entry. If you already have some information that might classify your chemical as being highly toxic in by a different route of entry, that could be relevant to know because it might avoid having to do some follow-up sort of testing by the inhalation route. And for those that are less familiar with these classification schemes, there's the global harmonized scheme that sort of outlines what different classes are associated with oral acute toxicity versus inhalation acute toxicity, and even dermal acute toxicity. And some work that Dan will be presenting has really sort of shown that if you have substances that have been classified as pretty toxic, so they've been labeled as GHS class 1 or class 2 by the oral route, they've tended to find that those are of equal or stricter GHS classification by the inhalation route. So one could imagine perhaps in terms of looking at the oral classification, maybe that doesn't necessitate doing some follow-up study by the inhalation route. So that's kind of one consideration to bear in mind. And a third one is really kind of thinking about your chemical in terms of what physical form it takes, whether it's a liquid, a vapor, or a solid. One can look at measurements or estimates of things like boiling point, melting point, and vapor pressure to make a determination of what your physical form of your substance is to begin with. And if you have something that is, say, a substance that's solid and in a powder form, things like the aerodynamic particle size that you could derive from a granulometry testing is kind of helpful to provide and assess what might be respirable and inhalable fractions. So if you have particles smaller than a certain size in diameter, whether you're going to inhale them easy and whether they can enter the respiratory tract by the nose or mouth. So they're just like 3 different types of considerations one might take before doing any testing. Switching gears then, there's another approach that one can take which really looks at sort of, you know, is the exposure level that one is concerned about, does that sort of, is there going to be any appreciable risk to human health in the first place? And there's something called the thresholds of toxicological concern, or the TTC, and this is a principle that really sort of establishes a human exposure threshold value for chemicals below which we don't expect any conceivable risk to human health. But this approach has really been derived on the basis of oral repeated dose toxicity information. But in recent years there's been a lot of some investigations to consider to what extent the principle of the TTC approach can be applied to other routes of entry. And there's been some interesting work back in 2009 by Philip Carthew et al. Who investigated consumer ingredients in aerosol formulations to see to what extent one could assign or derive TTC values below which there wouldn't be a concern to human health. And there was a follow-up study by Sylvia Escher looking at a different data set, the rep dose data set that was developed in the Fraunhofer Institute, and that's kind of available online and also in the OECD Toolbox. And they derived some different TTC values for inhalation. And most recently there's been a paper by Sylvia and colleagues that sort of did an updated analysis to rederive some TTC values in light of additional information. So that's another route that one can look at in terms of deriving values and providing some assessment of whether there is going to be a concern under the inhalation route or not. if we switch now, thinking about some of the in silico models themselves, I've tended to bin things in terms of whether a model is local, global, or some type of hybrid in nature. And actually there aren't really any, few if any, local models that have been developed for inhalation toxicity. Those that are available have been focused on volatile substances, and one example that was published by Cronin et al. Looked at the acute non-lethal neurotoxicity data for the neurotrophic effects of some solvents in rats and mice, and found that they could derive a relationship between that effect and using just characteristics like log KOW, boiling point, and molecular connectivity indices. But really kind of scouting around in terms of what models have been developed, they tend to be chemical class orientated and really looking at volatile substances. One can also take the approach of deriving a local QSAR model using data that might exist within the OECD Toolbox. So here one can conceivably go down the route of having a chemical that you're interested in, identifying some related analogs with acute inhalation toxicity, and performing an endpoint specific read across from those analogs. And this is a kind of an approach or a workflow, if you like, that can be readily accomplished using the OECD Toolbox. So here I've just sort of shown what the OECD Toolbox looks like, and there's a defined workflow that's defined in terms of you start with your input chemical, you do some profiling to identify what might be some flags for your chemical of interest. You pull out what available data might exist for your chemical, and then you go about identifying some related compounds, and that's kind of what's known as this category definition. And then the data gap filling can be done by 3 different modes, and the one here I've sort of highlighted is a trend analysis or a read across that can be done where you find these different analogs, and then you can make a sort of prediction for your given chemical. And on the screen it might not be all that clear, but your source or your target chemical here in this case is the red one, and then those that are included in the read across are the neighboring chemicals around there. So that might be a different approach in terms of using available data that exists within the toolbox to infer an LC50 value or some other measure of acute toxicity, and using other information for related chemicals. Okay. As far as expert systems or global models that exist, the only one I'm aware of that actually contains a log C50 acute inhalation model is that from the TopCat expert system, or known as toxicity prediction from computer-assisted technology. There is this one model. It contains 5 submodels that are related to different chemical classes, and I believe Dan has some slides where they've evaluated the performance of TopCat for their particular chemicals, and the results and the performance is rather mixed, I would say. So moving on from expert systems, another tactic that has been explored is doing what I would call a more mechanistic hybrid approach. And there was some interesting work that was presented at a McKim conference back in 2006, where the acute inhalation toxicity of some volatile neutral organics were found that they could be modeled using vapor pressure. And what Bife and Wallace and colleagues had done was really sort of pull together a good quality data set of acute inhalation information from rat studies, and then try and subcategorize those chemicals into different classes or modes of action, and something that was akin to the Vahar scheme, where you could kind of categorize chemicals on the basis of their modes of actions that have been defined for fish toxicity. And in that case, they had sort of a group for what were termed baseline narcotics, polar narcotics, unspecific reactant chemicals, like electrophilic chemicals, and then things that could sort of act by a specific mechanism. And if you did the grouping in that way, they were finding that they had some success in terms of they could build a model for the baseline narcosis chemicals, these volatile neutral organics, and they could model that with relation to vapor pressure. But if you had something that was acting by some reaction mechanism, but an unspecific one, such as if you had Michael acceptors, and they found that they could model that acute inhalation toxicity using a surrogate for experimental reactivity, and they use the GHS. And I've kind of I found their slides online actually. The presentation itself is called QSL-based prediction of inhalation toxicity, and they had a number of these modeling assumptions that they took. I've honed in really on the non-specific narcotic-like effects, where they had looked at sort of using vapor pressure or water solubility and chemical reactivity. And this was the original equation that they had defined, where they looked at vapor pressure in relation to the log of molar of the LC50 from these rat studies, and found that they could derive a nice correlation. And that work was subsequently published back in 2009 in ZAR and QSAR Environmental Research. What I haven't seen published, but was also articulated in the same presentation, was how they started to explore these other classes within the same data set to see if there were ways in which they could correlate that those particular chemicals with the LC50. And as I've already alluded to, what they found with these acrylates and methacrylates, these so-called Michael acceptors, they didn't find any relationship with vapor pressure, and these chemicals are highlighted in red in the figure. But they found that they could establish a nice correlation for using the GHS reactivity and relating that to LC50. And that kind of like raises some ideas in terms of, well, you know, there's some merit perhaps in exploring local models based on modes of action. And I think that kind of really reflects some of the ideas and thinking around using mechanistic information in terms of deriving in silico models in the future. The neutral organics model that Vife et al. had published, that has been incorporated in one of the commercial tools, and this is the same one I showed earlier. And within this pipeline there is a module that sort of looks at using the vapor pressure and making a prediction of acute inhalation tox. So there are some limited tools, but this is one that's been incorporated into an expert system for more routine use. So where can we go from here? And I was thinking, you know, what might be some future approaches to consider. And one I have in mind was based on work that we've actually been doing in-house, which is looking at trying to incorporate bioactivity information such as that will be generated from the high throughput screening assays from ToxCast or Tox21, and looking at using that type of information in addition to chemical structure information to derive local read-across predictions within a local neighborhood. And the work that we've been doing, we've termed GENRA, which sort of stands for a generalized read-across approach, and this is really just trying to predict the toxicity using a similarity-weighted activity of these neighbors within this local neighborhood, and just using these chemistry and bioactivities information as descriptors. Our work's been focusing on looking at trying to predict toxicity effects from different repeated dose toxicity studies, but I don't see any reason why we couldn't adapt that approach and explore it for other endpoints, like looking at some acute inhalation toxicity information. And the work that we've done here has just been published in Reg Tox Pharm, in case you're interested. The GENRA approach is really our attempt at trying to quantify the uncertainties associated with doing read across and moving it away from this qualitative subjective assessment, and in that end, our idea here is to sort of look at a chemical, see what its local neighborhood is with respect to chemical and bioactivity descriptors, and try and understand where we have greater or lesser scientific confidence in that prediction based on the number of nearest neighbors or how similar those particular chemicals are. And I think there's merit and promise in terms of trying to apply this approach for a number of different endpoints, including acute inhalation. Another idea or approach that could be explored is really sort of trying to categorize chemicals by their likely mode of action into neighborhoods, for which you could do a read across, or you could develop some type of QSAR model, but really trying to go beyond the ideas that were synthesized by Wallace and Gil Vive, who had used this Vihar-like aquatic fish toxicity type of framework. And I think this is something that Dan will talk much more about in terms of how their approach has sort of really moved this forward from this idea. And at that point, I would like to pause there and hand back to Amy to introduce Dan.
Great, thank you, Grace. Nice presentation. And as I mentioned, we will hold all of the questions until the very end after Dan's talk, but if you have any questions, please type them into the question box now. Speaking next will be Dr. Dan Wilson. Dan is a science leader in Chem Informatics at the Dow Chemical Company in Midland, Michigan. Dan's focus is on assessing and building predictive in silico approaches for mammalian toxicity, including acute toxicity. Dan's current seminar will address the research he has led at Dow in the area of predictive approaches for acute inhalation toxicology. The title of his talk is In Silico Approaches for Acute Inhalation Toxicity.
Hello, this is Dan Wilson from Dow. I'd like to thank Amy and Dave for the opportunity to share some of the work that we're doing, the research we're doing in acute inhalation toxicity modeling with various in silico approaches. And let's see, how do I advance my slides? There we go. So the scope of our work today is focused on acute mammalian toxicity via the inhalation exposure route. Acute inhalation toxicity studies are conducted either for product registration, product stewardship, or else to set acute exposure guidelines, either community exposure guidelines for emergency planning or in-house exposure guidelines. And at this point, there are no validated in vitro alternatives for acute inhalation toxicity. So the seminar will focus on in silico approaches to predict acute lethality by the inhalation route, understand potential mechanisms of high acute inhalation toxicity, and understand the impact of bioavailability. So an outline of my talk will be to go through information on the short-term exposure guidelines, differentiation between gases, vapors, aerosols, GHS category classifications, what we've done to build a database that we use in-house, some of our hypotheses, the distribution among GHS classes, QSAR modeling results, read across for inhalation tox, simulation of bioavailability, and then profiling by potential mechanisms. So on the screen, I won't go through all these, are a number of the various short-term exposure guidelines that are out there, and they're across different jurisdictions and for different uses, but essentially all of them really focus on using acute inhalation toxicity information to set various guidelines that would be either used occupationally or for community emergency exposure planning. And so some of the types of data that would be used from a regular guideline study, if we have an alternative, would also have to be amenable to fulfilling this type of information. As mentioned, really for inhalation studies, it's real important to understand the nature of the test material, whether it's a gas, vapor, or an aerosol. Gas is gas in a gaseous state at standard temperature and pressure. Vapors, it would be the gas phase of a volatile solid or liquid at standard temperature and pressure. An aerosol would really be a suspension of particles or liquid droplets or in air. And then to find the state of the material, it's really an operational definition that using the standard equations, of essentially looking down at the bottom, if the saturated vapor pressure is greater than 5 mg per liter, it'd be considered a vapor, unless we'd consider it an aerosol. And the reason this is important to make these distinctions is, as mentioned, that the GHS cutoff criteria vary depending on whether you have a gas, a vapor, or an aerosol. And in some of the databases that are out there that people may go to pull acute inhalation LC50 data from, it doesn't really give the distinction of whether the compound that was tested was one of these. So it's important then for the end user to be able to look at the information and derive which of the categories would best fit for a particular study. So as I mentioned, we've been focusing now on acute toxicity, including inhalation, and building large databases. As part of it, we curated our own data, and we also compiled various human inhalation exposure guideline values, compiled all these in Excel databases, and then pulled them into a master database in-house using Pipeline Pilot. And when we did this, we also, if we had other types of compounds that might not have had inhalation tox data, but they had other acute data, we added those, and then from those, using the CAS numbers, we extracted data from ChemID+, and when we extracted the data, we pulled not only the inhalation data, but we also pulled any other acute data by other routes. So this would include inhalation, oral, and intravenous. And the reason for the intravenous is that would be somewhat considered the gold standard, at least in terms of systemic bioavailability for compounds that may be absorbed and act systemically. It's an important distinguisher for inhalation tox that some compounds, at least that was one of our hypotheses, that would be more highly toxic by the inhalation route would be so by virtue of their targeting the respiratory epithelium. So it may not be a perfect correlation between IV and inhalation data, but I'll show some of our findings. And then we took all these databases once we pulled them together, and then people on the call anyone can go download the OECD Toolbox. It's freely available. But then once we did that, we set them in. You can populate it with your own inventory. So we've populated our in-house version with these as inventories. So if we have an unknown compound in-house and we're doing a read across or searching for data or analogs, it just better enables one-stop shopping because all this is sitting under one framework. When we curated the data, we pulled subject matter experts in inhalation toxicology together to make sure we did it the right way the first time. I should mention that I'm not an inhalation toxicologist by training. I'm a mammalian toxicologist, but now looking in terms of cheminformatics across all of the various ICIDs. So you can see on this screen a number of the data fields that we pulled together. It's also important to point out that some of the databases that are publicly available, they don't have all these data, and so there should be some discussion, down the road if more and more data become available to have some consensus amongst the types of fields that are pulled and where they're housed and that type of information. And then this is just a screenshot of when we were merging the information into Pipeline Pilot. And at the end of that exercise, we ended up with data on about 6,400 compounds, not all of them having acute inhalation data, but all of them having some type of inhalation data parameter that we could leverage in terms of read across or some type of predictive fashion. So our hypotheses were that compounds would be more evenly distributed across those GHS classes for acute inhalation than for acute oral. The reason being that this would avoid the attenuation of toxicity seen due to first-pass metabolism by the oral route, that the existing commercial global QSAR would in fact likely show poor predictivity, and we weren't really trying to pick on it. It's just that what we found is that currently there are no adequate global QSARs for any mammalian systemic effects. That third, if we accounted for bioavailability, we may be able to do read across between the inhalation and oral routes. Fourth, that the reactive mechanisms would contribute greater to the severity of acute inhalation than acute oral toxicity. And by reactive, we're typically talking about the reactions of electrophiles and nucleophiles. And then fifth, the acute toxicity of compounds acting via those reactive mechanisms or by simple physical properties may in fact be things that we could model just by plots of the toxicity versus log KOW. So firstly, just looking at the distribution of compounds in these databases I mentioned across the GHS categories. The purple line is the oral. As you can see, for the ones that we had inhalation data on, that there was a very marked predisposition to having most of the compounds be either GHS 4 or 5, whereas for the inhalation, either the 1-hour data or the 4-hour data, we see that most of the compounds were either GHS 1 or 2, with actually most being 1, and then pretty even, but a slight downward trend after that. As Tina mentioned, that when we looked at these data more closely, that we found that when compounds were GHS class 1 by the oral route, they were always GHS class 1 by the inhalation route. And when they were class 2 by the oral route, they were always 1 or 2 by the inhalation route. And so essentially, if you have a compound and you have an oral study on it, and it's GHS 1 or 2, we could probably likely recommend maybe just categorizing it as a GHS 1 by the inhalation route without having to run the study. When we assessed the global TopCat model, you can see the plot of the observed versus the predicted on the x-axis. And then this is the line that we got. The R squared of the line on this log plot is 0.33. And a better representation of the data is probably on this bar graph. So focusing down at the lower left, these would be all the compounds that were GHS 1 and then going across 2, 3, 4, 5. And we really want to be able to look at the GHS 1 and 2 compounds, which are the more highly toxic compounds. So for the GHS 1, we had 60 in our database that were GHS 1. 55 of those were considered in domain by the QSAR model, and yet of those, 55 of them were underpredicted. So it really was not able to distinguish the highly active GHS 1. When we look at GHS 2, we had 80, and most of those were in domain of the model, and yet about half of those were underpredicted. So really, when we looked at this, we kind of made up our minds almost just looking at whether or not it could get the GHS 1s or 2s right. And the reason for that is if we're going to use a non-testing method and a purely in silico method to categorize our compound, the one thing we want to ensure is that we don't miss the things that would be the more highly toxic compounds, which would be the GHS 1 and 2. And so part of what we then have been looking at is for QSAR models, trying to understand when they work and when they don't work, why they may not work. And so when we've looked real closely at this, and we actually look at a lot of compounds that Dow businesses would submit to our group from anywhere in the world, we've really tried to focus on distinguishing what some of the drivers are for the mechanisms that might cause the toxicity. And then this is just a one slide kind of showing how we're bitting these into different types of mechanisms. And then I don't have slides on it right now, but for a number of these, we're trying to digitize these into various databases that would interconnect and really focus on how then we might be able to work with others outside of Dow that are interested in building in vitro predictive models that would cover this landscape. But as you can see, broadly, reactive chelators, things that impact energy or protein synthesis, nucleotide synthesis, obvious effects on blood, ion and neural channel signaling, as well as some potent H receptor ligands or things that might bind and precipitate out in the kidney. When we looked at one of the databases, this would be the ChemID Plus, and we downloaded the data for the 4-hour rat compounds that we could get that were in our database that were the GHS1. These are the more highly toxic. We went through these just to start really picking apart and trying to understand what is the distribution of these that might be reactive versus hitting specific targets. And you can see we had 66 in the database that were GHS1. 72% of those would be reactive. So these would be things that would have the ability to obviously usually act like an electrophile. And so we also profiled these using some of the profiling tools out there to see if they were able to distinguish between the ones that are reactive versus some of the ones that might be hitting more specific targets down on the bottom. And essentially at this point in time, broadly they didn't. And part of the reason is they some of the ones down at the bottom are also being pulled into the profilers. But then looking down below, just the other 18, we see again a limited number of mechanisms for the highly acutely toxic. So things that would, the carbamates and the OPs inhibit cholinesterase, GABA receptor blockers, energy for mitochondria, protein synthesis inhibitors, anticoagulants, adrenergic receptor agonists, or one that would just interact and cause hypotension, do it signaling. But the other thing, and I don't have the numbers here, but we've also been looking at a lot of oral data for acute tox just to kind of do the same thing. And it's a work in progress, but what we're trying to do is to look at the 100 most toxic compounds in our database by both the oral and the inhalation route to see the distribution of the reactive versus the specific. And at this point in time, to the best of my knowledge, it's a much larger distribution of things that would be hitting the lung via reactive mechanisms that are the GHS1 than in the oral, where it's much more pronounced compounds that would be hitting specific mechanisms like the ones on the bottom. So we've also been looking at approaches for read across, one being route and second mechanisms for the route. We've investigated a number of different comparisons, but one being between inhalation and oral, inhalation and intravenous. We've plotted these. I'll show the plots. And then we've also, at least for oral, replotted after remodeling with a model to start trying to address bioavailability. For the mechanisms, as I said, largely either non-specific reactive or specific, and then some of the specific we can talk more about. So this is our plot when we plotted the data in our database for the intravenous versus the inhalation. We see R-squareds that are pretty good actually, 0.8, which is not surprising because the dogma would suggest that when administered by the inhalation route, compounds are often very highly readily bioavailable, and we haven't sat and look at the outliers to see if there's any other specific information that we may be able to have to refine this prediction at this point in time. Lots of stuff we yet want to do. When we looked at the oral versus the inhalation, we got an R-squared here of 0.33, and the little dotted red line is a perfect correlation that we just mocked the slide up with, and the actual trend line is the black line. And the units are in mgs per kg on both the X and Y axis. We show down as a little insert when we renormalize the data based on molar concentrations, the R-squared goes up to 0.42, so a little bit better. The reason we haven't done that throughout is when we're really trying to address being able to do read across for GHS, we're at the mercy of somewhat having to live with the units that were derived from some of the other types of guideline classification. So that's what we'll be showing. So then we took the data for the oral and the inhalation, and we ran a model that I mentioned which would simulate bioavailability by both the oral and in the inhalation route. This model is GastroPlus. I won't go through all of the information on the slide, but essentially it accounts for metabolic clearance using SIPs. You can see those here. It also accounts for the influence of the crossing the membranes, the various membranes, by both the oral and then the inhalation route. And then you have to populate it with some parameters to be able to even run the model. And so what we did is just to go in, pick one thing to do level setting. We picked for both the oral and inhalation dose a dose of 300 milligrams per kilogram for a 0.25 kilogram rat. We would have the opportunity in the future to go back and iteratively maybe refine that to see if some of the data I'm going to show might improve, or if it might improve for certain subsets of chemistry, but we just haven't done that yet. You also have to pick your particle sizes. For oral, we picked 10 microns, and then forget what we did for the inhalation. But it's 2 microns, there it is, diameter. And then we just have little schematics of some of the models down on the right side. So when we ran this, what you do is essentially, if the compound was originally assumed to be 100% bioavailable by either route, and the model predicts it might be 50%, it would move by 50% towards the origin on its axis. And so we just recurve fit the data on both the X and Y axis. And we see that when we did that, using the set of units I said that we'd stick with, the R squared went up just a little bit from the 0.33 to the 0.36. So slight improvement. What this probably didn't really address yet at all, and we're in the middle of looking at this more closely, would be the impact, as I mentioned, of the first pass effects, which are often very largely driven by hydrolysis and conjugation reactions. So what we are going to do as we start looking at this is remove esters and amides and potentially other hydrolyzable linkages, and then compounds that might be likely substrates for glucuronidation, for instance, where they would not be as bioavailable, certainly by the oral route, but we don't have those data at this point in time. Also mentioned that we thought that for things that would be different reactive subcategories, for here we have Michael-type acceptors, that we should be able to do a plot of log KOW and get a pretty decent plot within a regional set of chemistry. And that's an important point to distinguish. So by regional set, I mean we would pick all Michael-type acceptors, or alpha beta, or here another type, an acrylate. This would be an aldehyde or methacrylate. If you start crossing the boundaries of the chemical type, then it's less straightforward, the reason being that the influence within a subtype, for instance, of the unsaturated aldehydes, the electrophilicity within a given subset is pretty much very nearly a constant, but that doesn't hold true if you start crossing the subtypes. So here for the unsaturated aldehydes, we got R squared approaching 0.9. For the acrylates, an R squared of 0.8. And then, as I mentioned, if we take then within a subset and we replot it versus a descriptor that would account for the electrophilicity, and we re-examine the R squared, it goes way down to 0.1. So that really is telling us that within a series, the distinguisher is the bioavailability is reflected by the log KOW and not the electrophilicity. But if we start crossing chemistry boundaries, that might get more complex. We haven't tried to do those more complex plots now. Also similarly for non-reactive chemistries, where in our database we just took the simple hydrocarbons. You see the data on the top, and we plot those out. We got very high R squared, 0.93, and these would be compounds that would just be hydrophobic and then start being able to move in and out of membranes, and then ultimately at some dose have membrane type effects. So a summary then of the findings that we have at this point is that we really, when we pulled the data that we showed today, we focused on compounds that had actual 4-hour duration data. The reason for that is when you start looking at these databases, your own data, you'll see data from 7 hours or 1 hour or 15 minutes, depends on the, the compound and the study. And there's ways within acute inhalation to normalize those so that we could normalize everything for a 4-hour duration exposure. But we thought before we did that, the more robust data set obviously would be the guideline 4-hour duration studies. So that's really what we showed so far. That we found, secondly, a more even distribution among GHS classes for inhalation than oral, as we thought we might. That the GHS 1 and 2 oral compounds were of equal or stricter GHS class than inhalation. That the reactive compounds are contributing greater to the severity of inhalation than oral tox. I don't have hard numbers on that one at this point in time, so I'll have to come up with those in the future. That the commercial QSAR model showed inadequate sensitivity with R-squared. That's supposed to be 0.33. The plot of the acute inhalation tox to intravenous, the R-squared was 0.76, or for oral data, 0.33. And that when we ran the model through GastroPlus, it improved it slightly to 0.36. That the plots of the inhalation for various reactive species versus their log KOWs gave R-squareds of 0.8 to 0.9. That when we, on the other hand, plotted it versus a descriptor for their electrophilicity, the R-squared went down to 0.1. That the plots for the simple hydrocarbons were very high. I think we were at 0.93 if I remember. And that when we looked at the specific targets, that for the highly acutely toxic, we were finding limited targets. So they're either reactive, and most were, or they were just a few other targets, anticoagulants, mitochondria, things that would inhibit nerve transduction or protein synthesis. And so some of the planned future work then would be address the exposure durations, and as I mentioned, in addition to the 4-hour, as well as to do the conversions. We've actually done the conversions. We just haven't done the plots and any more curve fitting yet, where we normalize everything to 4-hour. There is a need for publicly available curated inhalation toxicity data. So there's a lot of behind-the-scenes dialogue going on as we speak regarding how to manage getting data out there and curated, and who would do the curation, where it would be housed, and who would donate it. And I think we'll hear more about that in the future. That, as I mentioned, we'd remove the potential hydrolyzable compounds, and then the ones that would be substrates for conjugation, and see if the read across between the oral and the inhalation improved. Examine the relationship of the mechanistic high throughput screening data that would either be in ToxCast or Tox21, for instance, to acute inhalation data, and especially define data gaps for predictive modeling. So if in that laundry list of potential specific mechanisms that we had, there's some that are, and there are some obvious ones, cholinesterase inhibition, for instance, that we could then start building regional models using those data, that would be very helpful. Or if there are other targets where we've identified the target, but there's not yet a high throughput screening assay, there'd be the opportunity to hopefully work with others, either at the US EPA or JRC, for instance, that might be able to come up with some high throughput in vitro models. And then there will be a workshop, as Amy and Dave, I think, have made everybody aware, focused with a subgroup of people later this year on really trying to define the science and the data gaps and the needs and how to move everything forward. I'd like to acknowledge the help of the personnel on this screen, especially the top two folks, Tyler Arnhammer and Amanda Parks, are the technical folks that work closely with me, that really pulled a lot of the data together, did the curation, did the databases and modeling, and helped with some of the slides. Mike Bartels, and down at the bottom, Fagan Zhang, really are working with the GastroPlus models and doing a lot to try to understand their utility for various routes, including inhalation. Barun Bhattarai was a postdoc here that he just left, but he really got us started with some of the work on building the databases in the pipeline pilot. Ed Carney was the founder of the group. Ed is unfortunately passed away last year, and as Pam Spencer has moved in very adequately into that role. And then our two SMEs in-house for inhalation tox are John Hotchkiss and Shannon Krieger. So with that, I have nothing else, but would entertain any questions. Thank you.
Okay, thanks very much, Dan and Grace, both. This is Dave Allen, as Amy mentioned, and the NICEDM support contract. Grace gave us a really nice overview of the landscape of how these in silico tools might be applied in an acute tox setting for inhalation exposures. And then Dan just provided a great overview of how Dow is applying these tools internally already. We do have one question that came through via the chat, and the question is, are mechanistic hybrid approaches approved by regulatory authorities, and what is the status of regulatory approval for this? So basically, I guess, basically the same question twice. So I'll throw that out for either for Dan or Grace. I do recall from our initial webinar from John Hotchkiss and Ian Indens, where they provided the regulatory landscape for inhalation tox, there was discussion of using these types of tools and information in a weight of evidence approach for maybe some waiver justifications. But I'll turn to Grace or Dan if you have other thoughts on that.
I'll let Grace go first, since she works for the EPA.
Yeah, but I have to bat it back to sort of Dan, and maybe even David can kind of comment, because my role here is purely scientific, and I can't really comment on what the policy implications are for the use of these within EPA.
So my thoughts would be that for doing non-animal testing for inhalation, as we mentioned, that if you have an oral study and it's highly acutely toxic, you could obviate likely out of the inhalation just by self-categorizing, classifying as a category 1. The other is if you had a lot of data either on compounds that would be metabolized to your compound or from yours, where you could do regional read across, where using data-rich and robust data sets, that it would be handled on a case-by-case basis. So at this point in time, my sense is that everything would be handled on a case-by-case basis depending on the jurisdiction, that people would be able to put their best case forward for why they would think an inhalation study might not be necessary, either based on some of the already given waiver criteria or the scientific information they may have, and then to work with the regulators to understand how that would work. But in terms of just open acceptance of any of these methods, a lot of what we're doing right now are very new and works in progress. So I think there's a way to go before the regulators are really on board with any type of improved in vitro or hybrid in silico in vitro approach.
Okay, great, thanks. And yeah, I think that is consistent with what we've certainly heard along the way, and that certainly valuable information that could be applied in a weight of evidence to make some decisions, but certainly not on their own. Dan, we have a specific question for you, asking if you could, I don't know if you're still driving or if Amy is driving at this point, but the request was to go back to slide 5 and explain again about the saturated vapor pressure determining form of exposure.
Yeah, that wasn't my slide. I did not have anything on saturated vapor pressure.
Okay, I apologize then. Great. Did you have anything on that? It specifically says slide 5 parentheses Dan, so I don't know what's on slide 5. I can't remember.
Oh, I can look on mine.
Are we able to go back to slide 5 on the screen?
Oh, okay, okay. Sorry, my bad.
Okay.
Okay, what was the question again? I apologize.
No problem. So could you explain again about the saturated vapor pressure determining form of exposure?
Oh, okay. So if you can determine the saturated vapor pressure using this equation, and so if you have access to like a study where you weren't part of running the study, and we're trying to figure out did they give a gas or a vapor or an aerosol, some of the equations here after the fact, you could go and just take your test material information, and then the rule of thumb based on the people that are subject matter experts in the realm of inhalation tox is that if it would be, once you run the numbers, that the saturated vapor pressure is something that's greater than 5 mg per liter, that you could then categorize it as likely being a vapor, whereas if it's less than 5 mg per liter, that would be an aerosol. Sorry. I thought there was a question on the modeling for saturated vapor pressure. Sorry.
Okay, great. Thanks for that clarification, Dan. So we're 2 minutes past, but I have one other question that if folks have time to stay on the line for a couple more minutes. The question for either you or Grace, Dan, is in the context of validation of the in silico models that are being used or may be used in the future. How can you comment on the variability in the animal test itself, the rodent acute inhalation tox study itself, and how that might impact on the validation of in silico models?
Well, I'll try to give my perspective on that, and I think that's a great question, and probably I'm glad someone asked that, because I think it's going to be really hard for a couple of reasons. And one of the reasons, especially there's some nuances of inhalation toxicology studies. And one is that when it's probably the one study type where it's as much as an art as a science to go manage running the studies and to get the material into something that the animals are breathing. And oftentimes what ends up happening is that they get an atmosphere that the animals could breathe, and they give that atmosphere, and there's no toxicity seen, and that number ends up in a database as having something where the LC50 is obviously higher than that. But we don't know how much higher. And so we may be able to use that type of information for a threshold, but we derive a threshold approach. As Grace mentioned, there's some thresholds being looked at. But in terms of building a real specific model where we'd be trying to train either a regression model or some in vitro assay against it, that would be hard. And when we looked at the numbers of compounds out there in databases like that, it's actually a much higher percent than we realize. So that's going to be one of the challenges. Another one is that when we've looked at, when we curated our data, that when you look at the data for a given set of chemistry where it may have been run more than once, maybe either in a rat or a mouse or over time, then you end up not necessarily always having where the numbers overlay one another perfectly. And so there would need to be some way to approach how do we manage, even when we've looked real closely at the data, trying to see, is there one study that's flawed or one that's not flawed, or was the way the vapor was generated in one study likely to give a higher concentration than another, and so it's going to be a challenge. And so because of that, really what I think the future will by necessity need to move towards is the ability to come up with a suite of in vitro assays that cover the landscape in some way to reasonably use that information to do read across to inhalation toxicology. And for the compounds that might be reactive, like the ones that we showed, or just simply by diffusion moving in and out of membranes like the ones we showed, I think it will be fairly straightforward, and we could probably get together now as a scientific community and derive those models. And for the ones that would be hitting specific targets, at this point in time, we probably don't have even enough in vitro target assays available, let alone data from those. And so I think the challenge would be to generate those data and then get powers that greater than myself that are interested in really trying to understand how do we relate this to the systemic exposure to things that might target the lung. If we think that the things that might target the lung the most are the reactives, and we're able to cover the reactives based on the model's work, and the others are likely hitting systemic targets, then we may be able to do read across to oral data or other data where we have much larger data sets, because there's a lot more oral data out there than there are inhalation data. And I think what we're not going to do to fix this is to have everybody run out and all of a sudden go run 5,000 new acute inhalation guideline animal studies and improve our database. So it's a very good question, and it's going to be a very interesting challenge and something that I think is really going to need to be figured out by the broad scientific community.
Okay, great answer. Thanks very much, Dan. Okay, with that, I think that concludes our webinar, the third in a series of 6, as Amy mentioned. Thanks again to Grace and Dan for taking the time to prepare and participate in today's webinar. Amy's got projected on the screen now the list of upcoming webinars, so please remember to mark your calendar for June 28th, where we'll have Marco Cavara from Dow Agro will come and will be available to talk to us about how they are applying the GH additivity rule in some of their internal decisions. Okay, well, thanks very much, and have a good rest of your Thursday. Bye-bye.
All right, thanks.
Thanks.